Greetings to all and welcome to this lecture. We are in module 7, lecture number 5. In this lecture, we will see what is effective mobility as per our MOS transistor is concerned. We will also see how this effective mobility is dependent on transverse field and how we can incorporate this effective mobility concept in drain current. These are the learning outcome of this lecture, which tells you the physical origin of effective mobility in MOSFETs and also tells you the role of phonon, Coulomb and surface roughness scattering mechanism across different transverse field regions. This lecture will help you to understand what is Mathesian rule and how to calculate the effective mobility following the Mathesian rule when all the mobility components are coming into the MOSFET operation. Let's do a quick recap before starting this lecture. In this previous lecture, we said that a MOS transistor can be operated in moderate inversion when its heavily inverted region will be in moderate inversion. For example, my source is operated in moderate inversion and drain is in weak inversion. So, this is weakly inverted, this is moderately inverted. My operation of MOSFET can be termed in as moderate inversion. We need to define a closed form equation which can be applicable in moderate inversion, because I cannot ignore simply the drift or diffusion component in moderate inversion. This moderate inversion modeling is hard. That is what we need to capture using some analysis, using some models, what we defined as soft plus function. We have seen that the current in the strong inversion can be given by drift component, which is nothing but W divided by L mu into COX dash into QI L dash square minus QI 0 dash square, and the current in the weak inversion can be given by IDS2 is equals to W into mu into phi t divided by L into QI L dash minus QI 0 dash. To maintain a proper continuity between weak and moderate and strong inversion, we define a new charge equation using this soft plus function as QIM, which is directly proportional to 2 into n into phi t log of 1 plus e to the power of VGS minus VT divided by 2n phi t, which defines as it will give you the value of e to the power of VGS minus VT divided by 2n phi t when this x, this function is small, and when this function is larger, this will give you what? VGS minus VT divided by 2n phi t, where 2n phi t and 2n phi t will get cancelled, and ultimately you will ended up the same equation what we were getting in strong inversion. Following these all, we derived a current equation which is applicable in general all region of operation. In general analysis of analog circuits, we consider the strong inversion model, and hence we have ignored the second part, which was VDS dependent in this equation, and we can say that this is a simple equation which can hold all region of inversion. In this lecture, let us discuss the mobility of the charge carrier during MOSFET operation. So, let us consider this is MOSFET and this is gate terminal, this is source terminal, this is drain terminal where you are applying VDS, and this is gate terminal and you are applying VGS. I am just tying the body and source as source to a same value. This is N plus, this is N plus, and this is P. So, this is general NMOS. When you apply the VGS, the inversion charge comes into picture, and these electrons will move because of the potential difference applied between drain and source. Now, how we can define the effective movement of these charge carrier inside the MOSFET? That is what we need to define a term mobility. We have already introduced this term earlier when we were discussing about drift velocity. We said that drift velocity is directly proportional to the field in x direction and this is y direction, right? So, we removed this proportionality sign and added a constant which we called it as mobility. So, mobility is defined as the ability of electron to move under the vicinity of all such mechanisms. where the unit of mobility is nothing but centimeter square per volt second. The best way to define the mobility or the effective mobility in terms of scattering. What is scattering is, first type of scattering we can define as phonon scattering. In general, the lattice vibration can be defined as phonon, lattice vibrations. It means, suppose you do have a semiconductor sample and you are providing the energy to this semiconductor sample. So the lattice, the atoms are vibrating, right? And in this vicinity, the electrons are moving in this direction, for say. Then the mobility of these electrons will get altered. If you increase the temperature, the vibration of the atoms will increase, and hence you can say the mobility decreases. So I can simply define the phonon scattering mobility is directly proportional to T to the power of minus 3 by 2. We are not going for a detailed derivation how this minus 3 by 2 term is coming up. It's simple as, if you increase the temperature, the mobility will decrease, which is phonon dominant, right? Or you can say lattice vibration mobility. The another type of scattering which is available in the semiconductor is Coulomb scattering, meaning suppose you have a semiconductor sample and you dope this sample with some impurity atoms, whether these impurity atoms are acceptor or donor. Under this vicinity, if the electron is coming into picture, then the mobility will get affected. The impurity scattering mobility can be defined as T to the power of 3 by 2 divided by Ni, where Ni is the impurity concentration. Meaning, suppose if I increase the impurity concentration, then what will happen? The electron which is moving from this direction to this direction, it will come under vicinity of multiple ions, and hence the mobility will decrease. The another type of scattering which is actually governed or actually found in MOSFETs is that surface roughness scattering. What it is, when you are applying the gate voltage, the electrons are coming near the surface, right? This surface is nothing but, or this interface is nothing but the interface of two dissimilar materials. One is silicon dioxide and one is silicon. Here I am talking only about silicon, but it is applicable in all type of MOSFET with different materials, right? So this is a surface of two different materials. One is oxide, one is semiconductor, and hence there will be a surface roughness. If you apply the gate voltage, right, because of this gate voltage, the electrons will go under the vicinity of this surface roughness as well as the transverse field. Thus, the mobility of charge carriers which is flowing between source to drain due to horizontal field, right, it will reduce. And this is a dominant mechanism in the MOSFET. So we briefly discussed that what is phonon scattering, what is Coulomb scattering, and what is surface roughness scattering. The good part of the Coulomb scattering is that when you apply VGS, some of the inversion charge come into the surface and they screen the Coulomb scattering. I will explain you how. Now let's see how the effective mobility varies with the effective voltage or effective field. Here this is our MOSFET, which is drain, source and the gate. The gate field is vertical and along the y direction, and this is x direction. So we are defining this field as E effective. Let us consider for a particular Na value, where Na is considered to be a substrate doping. So what will happen? First, due to Coulomb scattering, the mobility is lowered, but when you move towards the higher value of E effective, or when you increase the drain or gate voltage, then the mobility increases. Why this is so? Because of screening effect. Interestingly, it should be noted that the inversion charges screen the effect of Coulomb scattering, and hence the mobility increases. Let me explain you with this an example. For example, you have a MOSFET and you are applying a VGS which gives you 100 field lines. Out of these 100 field lines which are going from gate to surface, let us consider the 10 inversion electrons coming into picture. That is, you can say that you are in weak inversion. So what will happen? These 10 inversion electrons is actually affected because of these 100 field lines, correct? However, if I increase the VGS, and now you can say you are in strong inversion, so what will happen when you increase VGS? Let us consider the 1000 field lines are emanating from here, but in response to this 1000 field lines, you have, let's say, 10,000 electrons. Why? Because we have discussed earlier that my inversion charge is exponentially dependent on surface potential, or you can say psi s or psi y, right? It means when the surface potential increases beyond 2 phi f, the inversion charge increases exponentially. Now let us consider you have 10,000 inversion electrons. So the field lines which is emanating from the gate, which are 1000 in numbers, is, let's say, terminated at 1000 electrons in the channel. Now 9000 electrons will not face the difficulty of this Coulomb scattering. Thus we can say the inversion charge screen itself the effect of the Coulomb scattering, and hence the mobility increases. But beyond such point, what will happen? The phonon scattering dominates, because when you increase the voltage, the electric field increases, and hence the lattice vibration increases, the phonon scattering dominate, and hence the mobility is reduces. Beyond such point, if surface roughness increases, so in all probability the surface roughness mobility degradation dominates in the MOSFET. Now what will happen if you increase Na, or the Coulomb scattering can also be captured by the charges which are present in the oxide, which is trap charges. They also contribute in Coulomb scattering. But for the sake of simplicity, let us consider you are increasing the substrate doping. If you increase the substrate doping, then what will happen? First of all, because of the Coulomb scattering, the mobility is decreases. So that's what, there is a decline trend here. And the second thing is, if the substrate doping increases, the point which the inversion charge coming into picture sufficiently to screen the effect of Coulomb scattering will shift it to right side, which in a simple words you can say, if you increase Na, that is substrate doping, the threshold voltage will increases, and hence you need to have a higher voltage to cause that inversion. Those inversion charges which should be sufficiently enough to counterbalance the effect of Coulomb scattering, and hence this point is get shifted to the right, right? That is what this point will shift it downward, the mobility will increases like this, and ultimately the phonon scattering and then the surface roughness scattering dominate. Similarly, this can be plotted, which is dominated by Coulomb scattering at low fields, correct? Now can we make some formulation to introduce this effective mobility in our model? Let us define a simple formula considering the effective field having averaged out or having two components. One is EYS and one is EYB. I will explain you what they are. Let us consider you have a MOSFET, and between source and drain you have depletion region and inversion region. So to show this, let me change the color of my pen to blue. So this is inversion region. As we have already seen that the depletion and the inversion cause because of surface potential. So to define in the y direction, what we are saying, the field exactly at the surface, right, it is defined as EYS. Here S stands for surface, and there is another field which is just below the line of this inversion charge, just exactly at this point, which is defined as EYB, correct? Now I can apply a Gauss law to find out the relation of this charge and the electric field. You just consider a Gaussian surface and apply a Gauss law. So I am considering a Gaussian surface, one Gaussian surface as this to cover the inversion charge only, and one Gaussian surface to cover the whole charge, out of which if we rewrite this equation as EYS is equals to minus of Qi plus QB dash divided by epsilon s, right, where minus stands for negative charge. Epsilon s is the permittivity of silicon or semiconductor. It is 11.7 times of epsilon naught, which is 8.854 into 10 to the power of minus 14 farad per centimeter, correct. Now, what is E by B? E by B in the Gaussian surface, it will only consider the bulk charge, and hence E by B can be defined as minus of Q B dash divided by epsilon s. Now, a simple formula for E by effective is just to take a mean of it, right, or averaged out these fields. So, E effective can be defined as E by S plus E by B divided by 2. When you do so, you will get that the effective field which is experienced by these charges is nothing but minus of QB dash plus 0.5 times of QI dash divided by epsilon s. I am just adding these terms. So, one is this term and another is this term and just averaging it out, correct. So, this is an effective electric field. Now, we will see how we can relate with the mobility. First, let me introduce another factor which is NE, where NE is dependent on crystal orientation. In general, we consider that NE is 0.5, but based on the crystal orientation, the value of NE lies between 0.25 to 0.6, correct, and for electrons and 0.33 to 0.40 for holes. So, the mobility what we defined is now the function of effective electric field. If I want to calculate the overall effect of lattice vibration, impurity scattering, surface scattering, then I can use a Mathesian rule to calculate the overall mobility, which says that the mobility is given by 1 over mu plus 1 over mu 2 plus 1 over mu 3, where these mobilities are affected by following scatterings like Coulomb scattering, phonon scattering and surface roughness scattering. So, this will give me the overall mobility formula. Now, let us see how can we introduce this effective mobility concept in the drain current equation what we derived earlier. You remember that the drain current equation was derived as considering both drift and diffusion component are present in the channel. So, we can rewrite this equation as mu into W into minus of Qi dash into d psi s by dx plus mu into W into phi t into dQi by dx. This is diffusion component and this is drift component. Then we said that considering drift and diffusion component in the channel, you integrate between 0 to L. I ds dx is equals to integrate from psi s0 to psi sl into minus Qi dash into d psi s W into mu, right, plus integrate mu into phi t between Qi dash 0 to Qi dash L dQi dash. You remember in this equation we have taken mu out, considering mu is constant and it is not affected by the effective electric field. However, when we go for the derivation now, then as we have seen that the mobility is governed or affected by effective electric field, you cannot take it out. So, the correct way is you need to rewrite this equation considering mu inside the integration, and this is can be represented as mu as a function of E effective, where E effective now can be represented in terms of surface potential. And as we know that the surface potential inversion charge are interrelated. So, this equation becomes very much complex. You need to solve this equation in terms of surface potential, then E effective, then you need to solve this integration in terms of d psi s and dQi dash. Instead of that, simple approach is, let us consider under the vicinity of E effective, my mobility is now defined as E effective. It is same as the effective mass concept. That is what we are considering. All the scattering event is captured by the term mu effective and we are taking it out from the integral. So, I can redefine this equation as IDS is equals to W divided by L mu effective. into psi SL to psi SL minus Qi dash into d psi s plus phi t into Qi L dash minus Qi as dash 0. This is diffusion term, this is drift term. The only difference in this equation and this equation is what? We need to consider mu effective, where mu effective comprises all the dominant effect of scattering into the mobility parameter itself, right? Now, we can rewrite this equation as IDS including the mobility dependence is equals to IDS assuming constant mobility, just replace mu by mu effective. You can simply see that the equations are very much same, only difference is we need to replace mu by mu effective, and hence we can say the effective mobility concept or effective mobility effect is included in your drain current equation. Now, as the carriers are moving between source and drain, so the mobility also changes along this direction. So, can I define the effective mobility along the x direction? For doing so, what we are doing, we are rewriting the same equation again, which is nothing but the drift part plus the diffusion part, right? Instead of integrating, considering mu as constant, what we need to do is IDS divided by mu, and now you need to integrate. Why? Because mu is also changing along x. So, mu IDS by mu is equals to W into minus of Qi dash into d psi s plus W into phi t into dQi dash, right? And now we are just integrating with 0 to L dx, because mu is now function of dx also, or mu is varying along the x direction also, which is from source to drain, correct? So, following this, we can use this term W into minus Qi into delta psi by delta x plus W into phi t into delta Qi by delta x from the previous equation, right? You can rewrite this equation as IDS is constant, integration of 0 to L dx by mu, and this equation can be written as IDS into L by mu. From this equation, you can simply find out mu effective is equals to 1 over L integration 0 to L dx by mu, right? So, this is mu effective. Just do a quick check. If we considered mu is constant, take it out from the integral, you will left with 1 over mu into integration 1 over L 0 to L dx. This will give you L and L cancel, ultimately mu effective will be what? Mu. So, this is a simpler approach which helps us to introduce the effective mobility concept in our drain current equation, which we have already derived earlier. So, let me summarize here that the effective mobility concept is very important in MOSFET, because the inversion charge are governed by multiple scattering event near the surface. One is, we called it as phonon scattering, one is Coulomb scattering, and another is surface roughness scattering. We can use the effective mobility concept similar as the effective mass concept, in the sense we consider all the scattering event inside a parameter mu effective, and we will use this in a simple derived equation what we have derived earlier and taken out from the integral for simplicity. So, we can simply write mu effective into W divided by L integration psi s0 to psi sl minus of Qi dash into delta psi s plus integration of Qi0 dash to Qil dash into delta Qi dash into phi t, correct? In this lecture, we have also seen that Mathesian rule is given, which tells us how to calculate the effective mobility, which is governed by all the scattering events, be it either phonon, Coulomb or surface. So, we can simply calculate the overall mobility as 1 over mu1 plus 1 over mu2 plus 1 over mu3. Here mu1, mu2 and mu3 are actually governed by different kind of scatterings. So, we will stop here for today. Until then, take care.